Mir Mousavi from the Synchronized Energy. So he is the head of the advanced analytics and application at Synchronized Energy. He is responsible for the company's analytics, capability development, and strategic technology direction. He leads the multidisciplinary team of data scientists, power system engineers, and software developers dedicated to researching, developing, and delivering market-leading solutions for electric utility industry. Dr. Mousavi, before joining the Synchronized Energy, was the held various engineering roles at ABB, most recently at Global Technical Director and Executive Engineer in the Power Grids Division. Dr. Mousavi received his PhD degree in electrical engineering from Texas A&M University. He is an industry speaker, author, mentor, and panelist. He holds over 30 U.S. and international patents and has published several journal articles, conference papers, book chapters, and is a senior member of IEEE and has contributed to a number of PES technical working group. So Dr. Mousavi has done a lot to did so many aspects of the power system monitoring and situational awareness. So today we are really glad that he accepted to give us the talk. So with that, Mirasul, back to you. So floor is yours.
Okay, thanks very much, Saeed, and hello everyone. Thanks for joining us today in the session. I'm very pleased and humbled by the invitation of the team. We've got an hour worth of material. I like to invite questions in between the sections, so feel free to stop me anytime, and let's get some of those questions addressed, or you can wait until the end. We should have enough time for all of your questions. So before I guess I start, I'm gonna also optimize my bandwidth just to make sure that we stay connected. If there's any issues, obviously we are at the mercy of the grid. If any challenges on my side, I'll try to dial back in, but we had some scenarios lately, and I want to be cognizant of that. So again, appreciate the time. The topic of discussion today that I thought would be relevant, especially as we look for new ways of modernizing the grid and getting ahead of the challenges, I thought I would put this topic down, and something that I'm passionate about, but also it's been an area of focus in the last few years that I joined Synchronized Energy from ABB. So we're based in California. Well, we used to be in California. We have a head office now in Texas, but the origin of the company is in the Bay Area. Started as a hardware company making sensors and devices, and we move into solutions and an ecosystem development and essentially helping with modernization. So I'll talk a little bit more about what we do. So Saeed, I guess you mentioned all the background that's needed for me. So with that, let me just jump in with the agenda. So I guess keeping things simple, just again, focusing on a little bit of introduction about the company and what we do, a little bit about the background technology. I'm going to spend a lot of time on use cases, and this is an area that I'm also looking for help from your end. And I know that I'm talking to industry and academia and researchers, and I think we can help the industry move forward with definition and evangelizing some of these use cases. I will be especially focused on certain applications that I think are unique to the synchronized measurements. I think we can, and any measurement, any data is good, right? You can use it for many applications, but I'm going to focus especially on use cases that you can't really live or you can't really achieve without the synchronized measurements. So hopefully that will make sense. And of course, as a business and as engineers, we like to have fun and solve challenging problems. But at the end of the day, there needs to be business value to what we do. So I want to touch a little bit on business enablement from my own experience, transitioning from, let's say, a pure technology person to more of a half-baked in between, so to speak. Then I'll have closing and then Q&A at the end. As I mentioned, again, I welcome all the comments and questions. If you like, please interrupt me and I'll ask for help to just let me know if there are questions in the background, because I don't see if you raise your hands or have questions. So let's start with some basics. Introduction to the company and really what we do. We like to think of ourselves a lot more along the line of solution provider. We are a vertically integrated, let's say, IoT company, or IIoT, Industrial Internet of Things company. We make our own hardware, our own software, and our integration and application, for which I'm primarily responsible. And when it comes to the value really provided to our customers, we like to think of solutions, and depending upon how you slice it and dice it, you can put into one of the 5 major pillars of utilities missions: reliability improvement, safety enhancements, resiliency, efficiency enhancement, and of course, enabling sustainable growth and sustainable development. So these are some example use cases and solutions that today we provide with the solution that we provide and all that. It's not an exhaustive list. It's meant to just capture some of the highlights and some of the areas that we've been very helpful with our partners. So how do we actually do that? I use this slide pretty much as a quick overview of the architecture. Again, with leading with the solutions, the core in a capability is really the head-end software. We call it Ample. That's like an orchestration software that can go on-prem or increasingly can be deployed in the cloud. And it's really the system of record for communicating with end devices, communicating with other operational systems, providing a UI and user interface to the users, and kind of being the head-end software for all of the device management, OTAP, upgrades, what have you, essentially, right? So it's almost like a landing system that connects the rest of the components together to enable solution delivery. So on top of that, we have been building an advanced predictive capability, that mostly resides in the cloud, really taking advantage of the capabilities in the cloud for at-scale analytics, bringing data sources from our own devices, and then enriching and mixing up with other data, especially from other operational systems like OMS, weather, to really go after some of the industry challenges in terms of predictive applications. And I'm going to spend a lot of time on that piece of it, because that's been the focus area and an area that I believe personally that holds great promise in enabling breakthrough solutions. And that, last but not least, obviously, if this is all the show, the ticket to the show is the field devices. So those are what we like to call intelligent sensors and control devices that enable the data capture, especially the highly synchronized data capture from the field. So in terms of the depths and breadths of those devices, today we have essentially about 7 different product lines covering both overhead and underground, subtransmission and distribution. We're primarily playing in the distribution. That's where most of the visibility, most of the instrumentation needs are, as you can imagine. And so that's how we help. We also have a product line on grid edge control. I'm not going to, again, spend a whole lot of time, but that's an application where we support volt bar optimizations and help with efficiency improvements on the grid. So when we look at the depths and breadths of products, again, I like to think of, if you think of any use case or an area where there needs to be visibility and lack of data, we typically have a product line that can serve that purpose. So as an example, the top layer, the MM3s and MM3AIs and ZM1s, those are mostly overhead products, essentially. They go on bare conductors and 3 wires. And depending upon, of course, the application use case, there's different firmware and features that are enabled. Basically bring in fault data, load data, disturbance data, and in some cases, mechanical data, temperature, line temperature, what have you, so to speak. The 2 down below on the left-hand side are essentially our underground products. We call them UM3 Compact, and then on the right-hand side you see UM1. U stands for underground. So those are our underground products, and usually they go into switch cabinets, into transformer cabinets, and walls and manholes, and underground, above the ground. So we support submersible application. That's the newest addition to the family. And speaking of resiliency and being able to recover fast from grid events, especially due to natural disasters, we're finding that the submersible product being quite actually helpful in our customers' effort towards the resiliency. So in a nutshell, again, the collection of the portfolio of devices coupled with the head and software and the advanced analytics that happens at all three layers, including cloud, enables us to essentially deliver solutions that I mentioned earlier. Now, when we think about the application suites that basically then I'm primarily responsible with our team, we like to think of those that they come essentially in three buckets. In today's language, we call them descriptive, diagnostics, and predictive. So again, different application depends upon the use case and what problems we need to solve first. So descriptive applications are more about enabling our partners and customers and clients to be able to make more sense of the data they are bringing in terms of looking at fault information, abnormal fault events, looking at for fault detection and location and all that. Diagnostics applications are a lot about identifying issues with grid modeling, with load imbalance, with fleet health, harmonics issues, line loading, what have you. And the latest addition has been on the predictive side. I'll spend again more time on that in a little bit. So that's basically the intro, I guess, to the company. So I guess before I jumped into a little bit nitty-gritty and set some basic fundamentals on the technology side. So Saeed, do we have any questions or any comments from anyone?
Oh, not yet. I will let you know as soon as I see.
All right, sounds good.
Yeah, sure.
Okay, so here let's define the common currency of what we like to call the common currency of the grid, which is in a lot of advanced applications. It's really about disturbances. And the way that we define disturbances is very broad, more or less like any deviation from the norm on a cycle by cycle basis is considered a disturbance. Now, if you look at the history of the grid and how we started digitizing the grid, we started with the definition of what's fault and put SCADA systems and bring measurements and fault information, whether momentary or sustained, and those are fine, and we'll continue to rely on those systems. Obviously, we design a system to withstand fault conditions, but we don't like them to happen. So they are rare occurrences, but they're relatively easy to detect, easy to identify, just because that's how we design them, right? We want to make sure that there is enough overcurrent in the system that it kind of differentiates itself from the normal operation. So we have obviously great technologies and solutions that allow us to do what we do today to keep the lights on. Now, when we look at the disturbances, this is the untold story of what actually happens behind the scene that really up until recently, I guess, we really didn't have all the major enabling technologies to be able to shed light into really what actually happens in the days and weeks prior to a fault condition, so to speak, right? Just like human body, I think, a grid is almost a living and breathing kind of a being, essentially, and it actually presents ample signatures and ample anomalies before a fault condition occurs, that if you have the right instrumentation, the right analytics, and the right setup, we can pick these up and get ahead of the problems. And that's really the biggest promise of the predictive analytics, that with cloud computing, with wireless communication, and more importantly, synchronized and GPS level synchronization and data, now we pretty much have all the building blocks to enable these advanced applications and go after solving problems before actually they become problems. The challenge with disturbances, though, is they are abundant every day. I mean, every time that you can imagine you're flipping a switch, you're operating a piece of equipment, you're switching loads in and out, you're bringing EVs and solar, what have you. It is actually it's disturbing that sinusoid in a way, right? So you can imagine that 90% of the time, these things are normal and expected. Only 10%, maybe 5% of the time, things are abnormal. And the challenge or the key to success here is being able to identify what's normal and what's abnormal. And if you are successful in that, then we can essentially create a kind of forward-looking view of what's to come, not necessarily what actually has happened in the system. So if that's the currency, now let's define the characteristics of what we call synchronized transient measurements and how it is different from the other measurements in terms of SCADA or PMUs or phasor-based or dynamic type of measurements that we are accustomed to and use to a greater degree. So the key thing here is that we want to get to the high fidelity of representing the system as is and as designed, which is high resolution time domain representation of system states. So we're talking about highly synchronized, obviously the microsecond with the GPS clock, and also more importantly, also having a time stratum, because we know there might be times and where we might not have the perfect in sync with the GPS, and so time stratum is important so that we know when to use the data and when to maybe use it with the caution, so to speak. But the key thing, again, in terms of compare and contrast, is we like to see it at several locations. We like to have a highly synchronized, and we like to have a description of the quality of those measurements, so to speak. And then, of course, in this case, we're talking about the sample by sample measurements. And I believe that once we achieve mass penetration and mass deployment of these technologies, we've pretty much covered the entire space. The path forward from there is going to be just the resolution, right? And instead of doing 12-bit, can we do 24-bit and get even further and further into the details? But as you can imagine, for those of you that probably taken some transient courses in power systems, you're getting closer and closer to actually how the circuit actually operates and digitizing the analog world that way, so to speak. So those are really the fundamental. Sometimes I get questions of what is the minimum numbers and all that. So today we have a guidance that again, just thinking about balancing cost with respect to the benefits. We typically recommend one site every 3 to 5 linear circuit miles to get a kind of an optimal starting point and grow from there, so to speak. So before I go into the use case and all that, I like to maybe draw an analogy of why these measurements are important now and why now. And I guess I kind of covered the why now aspects of it, the confluence of enabling technologies. But the simplest way to think about these measurements are kind of draw an analogy between how successful we've been in the medical field, right, with an ecosystem of digital imaging that allow us to sort of understand problems and enable advanced diagnostics and prognostics, so to speak. Imagine a world where you don't have access and you don't have MRI technology or PET scan, essentially, right? I think it's not going to be too long where the grid is gonna benefit from its own digital imaging ecosystem. I think we have plenty of technologies today, as you can relate to operation technologies, IT technologies, metering, sensing, relaying, and all of that. And I think we take advantage of all of that. I guess the last mile in our measurement set is really going down to the transient level, and then more synchronized in those levels. So once we get all of that, I think that's going to be the ecosystem. And as I said, the path from there is going to be more increase in the resolution as the dynamics, as the behavior and characteristics are changing. Then we'll need to keep up with it in order to measure, monitor, control what we can today with slower speed and more of average time series based data that we rely on, so to speak. Okay, so I guess as I mentioned in my introductory remarks, no technology is complete without a view of the business case and what we should expect at the end of the day, right? Technology is fun, is cool, but we should be able to articulate what the value is and why we should invest time and effort into deployment of that. So One of the prime applications of synchronized measurements is really in the area of what I'm calling proactive outage and asset management. The traditional norm, as you can imagine today, is pretty much run to failure. Things happen, outage is registered, and then we go into the restoration mode. We need to figure out what happened, where it happened, dispatch the crew to the right person, and try best to restore what can be restored, and leave the system in abnormal condition, until the repairs can be done, right? So that's what we call business as usual. However, with this technology and being predictive around that, we enable the next level up, which is going from reactive to proactive. So with the data coming in, when it's processed rightfully, I mean, you obviously, the immediate benefit is cutting down the patrol time. So reducing SAIDI, most of our customers consistently report that they see an immediate about 10% or more reduction in their reliability metrics, which is it measures the duration of their outages. But we believe that really the major breakthrough is going to be to go even beyond that. And as opposed to waiting for things to happen and then figuring out how fast you can recover from it, why can't we see what's actually coming to us in a predictive way? And so it has a tremendous potential. Not only do you avoid the outage, and so all of your metrics go down to zero, no duration, no frequency, right? No MAFI, not even a momentary. But we also see that, addressing a problem, imagine addressing a problem at 2 o'clock in the morning compared to 2 o'clock in the afternoon. Which one is going to be more costly? And especially if you are prepared for it. So that's what that 70% comes in, that, you see the advancement in the reliability metrics, but you also cut a substantial amount of costs in addressing a particular outage if you can get ahead of it. And that's really what we are enabling, and what I believe is going to be a transformational change once it gets into full adoption, with the data that we are producing and generating in the grid today. Any questions or comments so far?
Not yet. So.
All right.
Yeah.
So.
Yeah.
I know I'm talking to technical teams and audiences, so I put this slide. Usually I kind of delete this because I end up usually spending about an hour or two. Maybe this is a session of its own, but just to give you a flavor of really the action behind the scene and what it really takes to go from data to business impact, what I'm calling. So. It involves multiple steps, and this is where I see a greater potential for a lot of AI, ML, and power systems. A lot of good old traditional signal processing, pattern recognition packaged into AI, ML these days. We've been doing this obviously for a long time, but now we have the benefit of contributions coming from other fields, and kind of speed of propagation, speed of deployments, and all that is astronomical. So that's another key enabler. I think this industry is immensely benefiting from the general, I would say, push and the general progress in the AI domain, and we can selectively apply to some of our use cases and amplify that impact, so to speak. But in a nutshell, it's a 5-step process with many steps in between. Again, I'll just keep it at a high level, and we can have a conversation after the fact, or you'll have my contact information for follow-ups and questions. Happy to address all of that. But essentially, it starts again with basic building blocks, which is the data sources, the transient measurements. As I mentioned earlier, maybe about 95% of the time things are normal. I mean, yes, there are disturbances. The systems are triggering and anomalies, but those are expected because the system is always going through transitioning from one state to another all the time, right? There are a few times where things are not normal. So one of the key enabling thing is being able to auto-classify and auto-label what is considered to be abnormal. So that requires obviously a lot of domain understanding of what we should expect if a capacitor band coming in and out, what we should expect if the regulator, what should we expect EVs is connected, right? A lot of that is translating the transient behavior of the system into data streams, and then figuring out how we actually automate that process and write scripts that allow us to auto-label things. So this is the first building block. Step number 2, then you kind of identify, okay, I've got a set of anomalies to work with, but usually there are a few cases where a single anomaly is good enough, but in many cases it's not, because the reality of it is that a lot of times, a lot of things will look alike. And so you're looking for substantial evidence. You're looking for statistical significance and all that. So that's why we take these things to the step number 3 in terms of looking at predictive modeling and alerting, where, again, we're looking for statistical deviations and some substantial evidence to suggest that an issue is coming up, because it keeps showing up and it's there. It's not going away. And ultimately, for the benefit of the dispatchers and planners and folks on the ground that will be the, let's say, the Sherlock Holmes of the industry, and go out and figure out, okay, what's causing it, or where this is coming from. We want to translate things into very simple traffic light kind of a concepts where, let's say, on a daily basis across the system that's instrumented, you put the data to action and then create a simple graphics that shows, with respect to the alerting and alarming and okay condition, where those sites are. So drawing attention to where it needs to be. So, I mean, at the end of the day, we'd like to make this as simple as just saying, go to line segment 1, 2, 3, or XYZ, and then look for equipment damage, for example, right? Take away all that complexity, because again, operators and planners, they can't be knitted with the data, and all of that needs to be translated into algorithms and applications and make it operational. So I guess in a nutshell, and again, without going into too much details, this is I guess the series of actions and processes that work together ultimately to provide us the sort of the lab report of the system states. And then, once we present this to the application engineers, we sometimes look at the grid models, look at other data set in order to kind of establish priorities, establish maybe a risk of failure, and drive them more towards a location, because detection is important, right? But obviously, if you can't guide the planners or the dispatchers to the right locations, it's not likely that they'll be able to find the source of the problem and address that, which is the most important thing, right? If you can't take an action, just knowing that there's something happening is just half of the story, perhaps less, so to speak. So without boring you with the high level stuff, I'd like to maybe use 2 examples to demonstrate a success story, so to speak, and what we can expect this technology at the masses to provide. So this is an example of vegetation use case. So again, the setup is pretty much the same across the board. You instrument the system, you start activating the anomaly detectors, and then the backend processing and all that happens. And ultimately, we end up seeing the picture that you see on the left-hand side with a pie chart of what is the composition of data on that day, so to speak. So every time we run this, these are typically processes that are running every day. And then you see that on a week prior to the alert day, we had 97% of the measurements coming in from across the system considered to be what we call operational. Again, normal happenings. Yes, they are anomalies. They are deviation from the norm. They're not sinusoid looking and all that, but they are expected, again, because loads are switching in. You have millions of things happen in the grid. But you see that ratio, right? Just pay attention to that ratio. It's 97 to 3. On the alert day, all of a sudden, that 3% jumps to 37%, right? So this is what I mean by substantial evidence. And usually, again, predictive modeling capability is all about just looking for this type of a rise, not necessarily just a frequency. There are other metrics, but this is the most important one that drives the alert. Once the alert is generated, then the rest of the process is all about figuring out where it's happening, what to do about it. And so again, in this case, the process usually is sending out somebody in the approximate locations, and if we usually ask them to come back with evidence of what they saw, and they came back with the evidence of burnt pine trees essentially touching the lawn, and that was the source, or that was what was contributing to that 37% rise in an anomaly, so to speak. So as you can imagine, detecting and identifying the issue. Not a problem.
Well, Caitlin, I told.
Thank you very much. Yeah, ultimately, the way that you get ahead of the problem, you want to affect the change management associated with how you actually take care of the vegetation. It's a significant spending. And now with this work, we're kind of moving towards spot treatment and kind of a surgical treatment. And you can imagine that in a wildfire scenario, if you can identify and get ahead of these problems, it's a very asymmetrical cost model. No amount of investment will come close to a catastrophe of another wildfire, so to speak. But in this case, we were not in the wildfire scenario, of course, but the impact was essentially avoiding the outage for 48 customers in this case, about 20,000 in this single incident. My next example is equipment related. Again, same process. In this case, before escalation, we were somewhere around 10% on the escalated days, which actually in this case, it happened 2 days on the 22nd and 30th of September. It was essentially dominating 67%. And the interesting story here is on the first time that they went out there after alert was issued, they were not successful in actually finding the problem. And it kind of speaks about the delicacy of sometimes with naked eyes, and they were not using special equipment yet at this level. So they came back, can't find the problem. And so we said, okay, well, we'll wait, because luckily some of these cases will reoccur and can wait, so to speak. And to that effect, 4 days later, we actually had a recloser momentary on the same circuit. Now, that momentary actually had enough fault current for us to be able to plug into the grid modeling tools and kind of get closer and closer to the potential location. And once that location was specifically identified, they were successful in the second run in figuring out that particular culprit. In this case, it was actually a cracked porcelain fuse cutout that was causing these. And in this case, because it was on the holding body, it would not cause the fuse to actually cause the outage. It would have caused the recloser to go into permanent or sustained outage, which would have impacted 138 customers in this case, with the potential CMI savings of about 60,000 on a single incident like this. CMI is the customer minute interrupted, which is oftentimes used to capture the value of outage avoidance or outage restoration times and all that. So, and then, of course, after the repairs, that's another confirmation. Usually we look into, well, if that was the main cause and we took care of the problem, we should see a reduction or back to normal, so to speak. And in this case, again, back to normal was, okay, we're down to 11%, essentially. So it's a confirmation that, we identified the source of the problem, we fixed it, and so another outage avoided, we kept the lights on. So I used 2 examples, but as you can imagine, from signatures and from disturbance and from measurement perspective, it can be any and all of the above, essentially. We usually think of them as 2 broad categories, either vegetation-related issues are predictable, and the second largest category is equipment-related. So those are the 2 major categories that, if you look at the outage data, primarily drive close to 50–60% of all of the outages, including weather-related. And granted, not all of these scenarios will lead into predictive alerts or will lead into precursor anomalies, what we call them. Sometimes things will happen out of the blue, and of course, we have our current system to take care of those scenarios. But in the vast majority of the cases, the system is speaking to us. It's providing the signatures, providing the signs of heart failure, so to speak, right? And if we have the right imaging and the right analysis tools and technologies, we can get ahead of these problems and be successful in avoiding the outage for all the good reasons. So this is, I think, the end of my first part of the presentation in one of the, I think, key use cases that, again, exclusively and very predominantly relies on synchronized measurements to be valuable. I guess before I jump into the second segment, Saeed, any questions or anyone has any comments?
Any comments? Not yet. Yeah, not yet. So
Okay, we're good. All right, so I guess my second part is going to be just a little bit of what I'm calling a lightning round. Quickly go over some other use cases that hopefully will entice some of you to maybe take a closer look at, what you can do with your contribution to the industry, to the work that you're doing, and any partnership. We're always looking for doing more with the partners and the innovation ecosystem. So they're not meant to be exhaustive, but certainly, again, I focus on specific application that, again, exclusively benefits from synchronized measurements. One is, as you heard me talking about location. So the two views on the right-hand side kind of gives you the whole story. If you don't have, let's say the upstream view, in this case, captured the sub-cycle event. And all we know at this point is it's downstream of it. But as you can imagine, in circuits, we've got miles and miles to patrol. And, if it doesn't cause an outage, we don't know really what is happening. All we know is it's downstream from this site. And, I've seen circuits that are 50, 60 miles. So I guess good luck finding that. But you can immediately see that now if you have a downstream view, it's very clear in the pictures, and I invite my signal processing gurus to figure out how do we do this automatically. Obviously, visually, it's very easy to see, but I can tell you that it wasn't that easy to just program this in. But it's there, and that's one way that we can utilize this data to be able to get closer to location. I submit to you that this remains to be one of industry grand challenges, and I think we've taken the first step. I think we can identify the zone or segment, but I oftentimes get questions about, oh, can you give us a distance? And I'm like, well, not really, not yet. We haven't, I guess, even for fault location by distance, I think in distribution system, we still have a lot of room to improvement, let alone on disturbances and anomalies like this. So it remains to be one of the grand challenges that hopefully we'll solve as we make progress on this front. My next use case is about the tap changers. As we see, the need for voltage regulation and efficiency and optimization is going up. We're going to operate these devices more often. Capacitor banks are switching more often. Tap changers the same way, and EVs and solar and DERs in particular are changing the operating paradigm. So while these devices have been very reliable, I would say, over the last decades, with increased operation comes the risk of premature failures. So this is an example of a particular, I guess, failure pattern that relates to the tap changer, where instead of making before breaking to the next tab, it actually breaks before makes. And you can't have that. It'll create market arcing, and over time, it'll basically cause the total failure. The signature is very, very vivid in this case. You just have few sample points of no current almost if you are sitting right upstream of the regulator, so to speak. A little bit of a drop in the voltage, but that is it essentially. So the good news is that it can stay in the system for some time, and I think that's exactly what happened in one of our recent cases. We had a circuit with two back-to-back regulators with a little bit of load between the two, and we identified the anomaly. We started the process of figuring out what it is, and in this case, again, because it's a control device, you can essentially do a little bit more in terms of kind of recreating the scenario. So the team was able to manually kind of switch the taps up and down and kind of recreate the signature, right? So it allowed us, again, to kind of identify that, okay, it's coming from these two regulators, but okay, which one, right? Because you can't just go and replace them, right? You just figure out which one it is, and it took some time to actually kind of put one in the manual mode and switch the other one. But at the end of the day, kudos to the team and to our utility partner. In this case, they were successful in kind of pinpointing the failing regulator and put it in the manual mode. But again, all enabled by the measurements that otherwise would not be available. And even if it's happening from upstream or from substation perspective, it'll be very hard to pinpoint because the signature is not unique to tap changers. You could have a loose disconnect switch that briefly disconnects and briefly cause interruption, and could be similar in many ways. Moving on, the next use case, I would say, unique to these measurements is oftentimes, again, deals with the control equipment, especially capacitor banks. Again, we see this a lot more kind of, raising or rising failure rates, because again, these devices are being operated more. And in this particular case, we're looking for a potential fuse protection that kind of takes out one phase. And so if you have the synchronized measurements from the system, you can actually do a little bit of a math on it, and because it's a steady state kind of a change, so this is not completely transient. But you're looking for, two phases making the correction. I see an angle change. That's what's expected to see in the measurements and data. And the third phase isn't doing it. And by the way, it's doing it every time it's operating that. It could be, because again, you expect a daily operation, so you don't necessarily have to wait for just one only, but you can keep watching it. And once you have 2 or 3 successful identification that one phase is missing to correct the angle, then it's very evident that there's a potential switching failure, and you can take care of it. It's interesting that, again, with all of the instrumentation and controls that we have, we don't really monitor for these kind of scenarios, and these things can go unnoticed for extended amount of time, and we feel like the system should be okay, but it isn't really, because it's been compromised in this way. For, again, some of our hardcore power system engineers, I'd like to maybe bring up the cold load pickup. We know what this is. We've seen in the textbooks. We know what it looks like, but it's interesting to see that the impact and how much bad inrush or how much rise you're going to see in the first few cycles is very much location dependent. It's very much dependent upon the presence of the DERs and what have you. So one of the advantage of having synchronized measurements is just getting into the details, looking at the XOR ratios, looking at potential nuisance trips, and whether understanding whether it's an expected behavior or not. Again, during the design phase, we take care of all of these things, but as the characteristics of the feeders and the system is changing, we don't know how the response of the system is changing. And these measurements and this level of granular data allows us to kind of articulate the changes, and then potentially send an alert or raise the question to protection, to designers to take proactive actions and avoiding a bad outcome, so to speak. Specifically with DERs, so I would say that if nothing else, really, DERs of all types, both traditional and IBR-based, inverter-based resources, will definitely be an order of magnitude increase the necessity for this level of measurements. I think it's recognized within IEEE PES and other bodies that we don't know what we don't know. Obviously, again, we design per the spec. We design for all the good things, but we don't know actually what's happened in the field, especially as you are integrating with a, let's say, legacy system that really wasn't designed to coexist with the new types of generation. So I guess the question always is, well, what do we know about the start and stop time? What do we know about the ramp up, the ramp down, ramp rates? Essentially, the graph that you see is an actual measurements from a circuit that had the DER on it. I think this was a cogen facility, if I'm not mistaken. We have similar example on a solar circuit where during the DER off, you see a complete balance between voltage and current, great power factor, things are in tandem and all that. And there are times where you are at the grid parity. And as you can imagine, when the DR is on at the grid parity, you really don't have any current flow and you have the voltage, right? But the blue is the exchange of the current essentially between the two sources, and it's not even sinusoid. I did ask the team to do a harmonic analysis, and the red on the right-hand side is really the harmonic contents of that that blue trace in the bottom. About 140% of fundamental. Obviously, that's not real. That's just the residual current and to some extent measurement noise added to it. But again, it kind of shows how much fluctuation you can have on any given day between two sources as you're ramping up or ramping down based upon grid conditions or based upon the generation itself, so to speak. Now, what do we know about the point of parity, when it's happening, and to what extent we are adhering to interconnection requirements? All of these things enabled by these measurements. So first thing, observe. Second, support the analysis. And then there are times, and I won't be surprised that at some point we run into abnormal behavior, both on the grid side, on the DR controls, what have you. And so we want to understand when it's happening and, again, creating the right alert so that we can get ahead of these type of problems. I guess the next use case is real quick on a little bit of unconventional circuits. We still have a good population of circuit topologies that what I'm calling effectively ungrounded, so either not grounded at all or grounded through high Z. And as you can imagine, when you are dealing with an ungrounded circuit, you don't have fault currents. That's the whole purpose of the design, so to speak. So you don't have the overcurrent protection. You can't detect it as a fault, but you can continue to operate the system. But you don't want to wait too long because you're risking safety, and also you're running into the risk of second fault, creating an overcurrent event and all that. So how do we actually detect a single phase to ground fault, if you want to call it? Although it's not a fault, it's essentially a disturbance. It's a capacity discharge when it happens. That's a very unique use case that, again, synchronized measurements allow us to detect, but more importantly, locate. Because again, detection is always 50% of the story. We need to also locate what is happening, and here is an example of a capacity discharge because of a ground condition on a 3-wire circuit. And as you can imagine, at the time that the contact is made to the ground, you really have a small window of opportunity in looking at that capacity discharge. And the only indication is gonna be there that if you are upstream, you're gonna see a little bit of a rise, at the time of the contact, and the downstream side will see a little bit of a discharge in the opposite direction. And that's all you're gonna get, so to speak. So if you don't see it, if you don't capture it, imagine if you put an RMS filter on it, it's pretty much at the noise level, right? It won't be noticeable. And so it's another use case, a very special one that I think definitely requires synchronized measurements from at least 2 sites to be able to detect and successfully locate these events. Finally, I'd like to leave you with some, I guess, thought-provoking things. I oftentimes hear that, what if we just to put a lot of good instrumentation at the substation level? The reality of it is that, what you see and what you don't see may surprise you. It's definitely needed. We need to see everything from head of the feeder, but it's not going to look the same, and so we may not have the same level of success. And this is a particular example that kind of illustrates that. So in this case, we have 3 sites. Let's say one is about 4 or 5 miles down from the second one, which is about 5,000, about a mile down from the substation. You see all the parameters and all that. I'll just maybe draw your attention to the XOR ratio. From 4.5, we're dropping down to 2.5 in the second side and 0.74 at third side. So the circuit is becoming a lot more resistive as expected, so to speak, right? So imagine if a disturbance, not even a fault, if a small subcycle event happens on B phase downstream of site 3, what do you think we're going to see at site 2 and site 1, right? Okay, so if this is a fault, most likely what we say, okay, ignore all the loads, the fault is going to be the predominant, and you're going to see the same thing, right? The source to socket, you're going to see the same, relatively speaking, similar type of start and end time and magnitudes and all that. And that's what we've been using for a lot of our fault studies successfully, and we'll continue to do that. But the story is quite different if you look at a subcycle event like this, right? So you see on the right-hand side, this is what site 3 sees for the same event, RMS of 9 amperes, peaking at 80 amperes for a crest factor, which is the ratio of the two, 8.2. You move up to the site 2, about 15,000 feet away, all of a sudden, you are at 101 amp as far as the peak, with a crest factor of 3.1, because the loads get added, right? And if you move all the way up to site 1, now that vivid spike in the current is pretty much embedded within your regular measurement. You can't even, well, you can visually, I guess, see it, but it's very hard to discern that it's actually happening, and it's actually quite significant, 15 or 20,000 feet down the road, so to speak, right? So it just goes to show that, again, that's why we need distributed measurements. That's why we also need synchronization. In this case, we are at at the microseconds. There is actually a propagation delay. You could see that in the waveform, but nonetheless, exact same moment, we see same picture at different site with the different attributes, so to speak. So it's one of the prime reasons why oftentimes I advise our clients that what you see and what you don't see. What you don't see is what you want to worry about, and and oftentimes getting closer to where the action is the key to success, so to speak. All right. No technology is complete without talking about change management. So I'm going to spend the last few minutes in the soft side of things. And so, and again, all of the technology is enabler. So in order to make really an impact from engineering and business perspective, a lot of these technologies will require a degree of change management. And as the code says, it's the only constant in life. You can't resist the change. It's going to happen. But we can facilitate the change, embrace it by strategic planning, making sure that the stakeholder buy-in is there, and then developing an ecosystem and collaborating with the partners. That's been our recipe, that's been our success, and that's what I would advocate when we introduce new technologies into the grid and would like to have accelerated adoption. So with that, I'll leave you with that really 3 takeaways in no particular order. That I believe that the time for utilizing synchronized transient measurements and disturbances is here. Enabling technologies are there, and it's provides a really unique and best opportunity for us to go after some of the unsolvable or difficult to solve problems, as I indicated in my presentation. It's going to require a lot of strategic and tactical partnerships. But at the end of the day, I think that the next revolution or the next breakthrough in grid modernization is really going to come from how we go from reactive mode of operation today when it comes to modeling, planning, and operation to really predictive applications across the board, so to speak. So with that, I'll turn it over to you with any questions and comments, and I'll look forward to potential partnerships. And as I said, we're not gonna win this battle alone, so to speak. We've got great partners, and if you think of an idea or use case or an opportunity where we can go after and demonstrate and help with the adoption, you've got my contact information available at any time. So thanks so much for your attention. I guess we could open for a Q&A.
Yeah, thanks a lot. Yeah, thank you, Mira. So that was very engaging talk. We really appreciate that. So let's go first with people online. If any people online, if you have questions, please unmute yourself and ask your question. No? Okay, so let's go back to the people in the room. So I should mention that Dr. Miras, when I was a PhD student, Dr. Miras was the program manager at ABB, and basically my project was funded by his group. So we had monthly meeting. So I waited 15 years. So that's become our turn. So we have to ask a question from you.
I hope we didn't give you enough hard time. It's revenge time.
Yeah, that's it. Right. I just waited for this for 15 years. So let's go by good questions. Very good question. Maybe I can start. So that is really cool technology you guys are working on. I had a PhD student. He also worked on the, later on I will talk to you for the details. So basically we wanted to pinpoint the incipient fault using this synchronized sampling. So here, when you're saying that when you detect a fault, do you mean that you pinpoint the location or you identify the faulted section? So,
yeah, no, I think in reality it's somewhere in between, and it oftentimes determined by the duration of that particular event, so to speak, right? So if there are enough data points and the sensing locations or the measurement points are conducive to performing maybe the reverse transient analysis, okay, under what condition I can get these measurements, we can do a reverse calculation, and that typically gets you in the vicinity. So that's probably the best outcome and the best scenario. Otherwise, let's say if it's a short cycle and there's not enough data points, or the parameters are unknown, or there is too many laterals or too many line segments between the two sites, then really the best you can achieve is identifying who's upstream of me, who's downstream of me, and then kind of going after the zone of interest. And that's what I think drives also the density in the number of measurement points. So we do recommend that when you have bifurcation, the circuits, like you have a three-phase coming in and it kind of splits into two pieces, that's where you want to put a measurement point there, because when you talk about the segment, then if you have a bifurcation, then you have now two options. You can go left or right, which way you're going to go. And if you don't have measurements, you have to, and again, if it's a large area especially, you may need to patrol a larger area, and that adds to the time, so to speak. So practically speaking, it's a by zone, especially. I mean, but if the other scenario that I mentioned, when we had a fault current, it advanced enough that it creates fault current, then you can do traditional fault location, get closer to the action.
Okay, that's nice. Also, as I see, I'm not sure if you also explored, for example, high impedance fault detection, down conductor fault detection type of thing.
Right. Yeah, I think those are, let's say, within realm of possibility. We certainly register and capture many of these events. I think to convert that into highly reliable, trustworthy application, I would say that it takes a lot more data. It takes a lot more characterization work to make sure that, again, you're not getting confused by other things. I mean, I've done work in high-Z, and yeah, it's very difficult to uniquely characterize. And of course, with the level of data now, with the details, obviously we've got more opportunities than in the past to go and solve that problem. But I would say that I don't think that I would put that at the same maturity level of other applications.
How about, maybe that's my last question. You guys can think of other questions. So how about if you compare the cost of implementation, because I don't know how much is, for example, is different from the just conventional, for example, fault indicators, or how many times is more?
Yeah.
Have both voltage and current measurement. Is it the case? So
right. Yeah. Well, that's another big, I guess, consideration, that a lot of the hardware that I discussed earlier, in many cases, they can go on the line and be operational in 20 minutes, 30 minutes, so to speak, right? They're fully autonomous. I like to think of them as iPhones and wires. There's no wires going in, no wires coming in. It's all wirelessly enabled. It harvests the power also from the line, and so for that reason, comparatively speaking, with respect to the data and the capability that it brings, it's like basically putting an oscilloscope on the line, so to speak, right? And then once you start leveraging the data set for multiple value streams and multiple applications, when you divide all those benefits compared to the cost, it actually becomes a lot more commercially viable and more valuable than having a single device that only does one particular function, so to speak, right? So when it comes to deployment scenarios and justification for the investments, being able to leverage the same infrastructure and same deployment for multiple use cases allow us to reduce the overall cost and make it viable, so to speak.
Yeah, sure. Oh, that is really interesting. Anybody?
This is Brent Carper. I have just one question about GPS time accuracy when you're doing these types of things. It's fantastic. We're seeing more and more distribution devices that have built-in GPS time, but it's usually traditional iRig-B. It's fantastic for fault synchronization and event analysis, that kind of stuff, but it may not be GPS time accurate enough for synchrophaser, and I'm suspecting not time accurate enough for the stuff you're doing. We have to take it to the next level of time. So is that something you face with your device?
Yeah. That's an important consideration. In fact, I guess the ranges needs to be in the microseconds for sure. If you are at the milliseconds, if you're using network time or you're using iRig-B and other data synchronizations, and you're looking for what I'm calling average RMS type calculation, sure, that can work. But when we look at the sample by sample correlation across multiple sites, every microseconds help and is important. So that's why the chipset that we use in our devices have embedded wireless with a true, basically high-fidelity GPS antenna with them that allow us to pretty much meet the requirements in terms of time synchronization.
Every device has to do its own time synchronization. You can't rely on networked time.
No, absolutely. Now there is a fallback to it. So we have actually, that's why I think Stratum is important, because there's like 5 different levels of quality. The best one is, hey, I'm locked into GPS and I have my independent internal clock. Every sample is pulse per second measured and timestamped, right? Now, if for whatever reason you lose it, or a foreign object is destructive, you revert to the second option, and then third and fourth and fifth. But the device has that attribute. So in some applications, it's not that important, right? You can live by a few milliseconds. But in other application, if you know the time stratum is 5, which is the lowest quality, you don't want to mix that data with the time stratum of 1. You just have like a level of confidence that you're going to express that, hey, this result may be impacted by a time accuracy of 5, so to speak. So we manage that, but yes, in our devices, every device has its own internal GPS synchronized clock to be able to independently timestamp the data.
Okay, that makes perfect sense. Thank you.
Absolutely.
Good. Yeah, Miraj, Brent is has extensive background on the protections and so on and so forth. So that was very into the point of question.
Brent, what organization you're from?
I'm with 3AC Engineering. We're just a 2-person consulting, primarily protection engineering. Lots of substation, transmission, distribution, relaying, kind of specialize in relay upgrades and some of that kind of stuff. So,
yeah,
I'm on the wildfire side, I'm seeing cooperative small utilities investing heavily in state-of-the-art reclosers, and we're getting some technology out there in the distribution system that allows us to do awesome things, right? I mean, it was really hard to get good data out of the old hydraulic reclosers. So we're moving forward, but I'm a little bit concerned that they're not. It wouldn't cost that much more to put a very high accuracy time source into a line recloser, and now we could maybe do it for something more.
Correct.
That's kind of why I ask. I think there's we're moving in the right direction, but there's a small incremental thing that could be done that would help out, even like what you're talking about.
Right. Yeah, I mean, new application definitely, right? It makes sense. But I think in a lot of scenarios where things are like a no-brainer is actually, like you said, providing, crawl, walk, and run. If run is okay, I have everything that I need. The walk is, well, how can I get quickly, let's call it, digitize my hydraulic reclosers? And that's actually a perfect scenario where, for retrofit applications, it kind of provides a transition point without a huge amount of investment in getting the benefits of a full investment, but without really ripping apart all of the legacy devices. And that's where actually we see a lot more success in the business as well. That instead of, if you can't do 2.0, the 1.5 is let's digitize your existing devices with the solutions that kind of takes you there essentially. So yeah, very valid use case.
And I couldn't agree more with your from a business perspective. We can't do a device or a solution that does one and only one thing. The bang for the buck is when you can do something that can solve 8 problems or something like that. That's where it all comes together.
Yeah.
Very cool.
Yeah. It's always in the constraints.
Yes. All right. Thank you for a great presentation. Really enjoyed it.
Absolutely.
Guys have question? You have one?
Thank you for the great presentation, Dr. Mir. All the use cases you covered were like really impressive. And we can clearly see that if you place your data collectors everywhere, then you collect those data and you can zero in onto your problem. So what you are doing. That is awesome. So my question, like I have actually two questions. So my first question is like you are giving us like a higher level overview based on various use cases you mentioned. So what since you are not you are saying you are using your own devices and like let's say not just if at all PMUs. So what state variables are you analyzing? Like, is it just like voltage, currents, frequency, or is it?
Yeah, no, it's primarily it's primarily voltage, current. As I mentioned, in some cases, line temperature is tagged as well, line loading, and of course, when we're talking about voltage, in our low voltage and in grid edge control device, we have access to the direct voltage measurement. The overhead products actually don't even do voltage directly. It's what's called the E field because there's no reference to the ground. And there's obviously from technology perspective or from challenge, it's another level of challenge that we had to revisit some basic fundamental power system engineering because everybody knows voltage, but hey, what is the E field and how is it different from voltage? And so we've actually published some papers. You can look it up in terms of how do you basically doing a special treatment of the E field to approximate the voltage without jeopardizing the application benefits. And it turns out that, again, when we look at the transient behavior and the window of attention is not long, we're talking about cycles of data, all the external factors can influence E field are accounted for. And so when you look at the cycle to cycle change, the relative change between E field and voltage are very proportional. And so that's a benefit, and that's what we leverage to then say, look, for example, in the capacitive bank switching, when if we want to look at the angle difference, well, in the few cycles that the transient is occurring, whatever external factors impacting E field to be different than the voltage are the same. So if you remove that common denominator, the angle shift before and after is going to exactly match with the voltage shift. So for that application, that relative and that differential view of the data allows us to actually enable the application without being concerned with the proxy approximation of the voltage. So anyway, I hope that helps a little bit, but it varies across the board. And again, it's at the end of the day, it's a compromise, so to speak. Again, voltage measurement on MV is very difficult. I wouldn't say it's difficult. It's very costly, especially if you want to do at multiple sites and all that. And so you have to just, again, just do what we can. And interestingly, it has some interesting challenges that we had to overcome.
Thank you for explaining that. So, and my second question is like, I actually missed how you tackled your, the very first use case you mentioned, which was like some vegetation wildfire issue. Like, so surely all your like your mechanism is analyzing like time series and stuff, right? And surely not any image analysis, or is there image analysis?
No image. It's all it's almost like, I don't know if I've learned these things recently, I guess, but in the market, you notice how technical and analysts say, hey, I don't need to know about the fundamental of business. All of that translates into the pricing. And if I can just look at the price and how it's changing, it consider all of the fundamentals of a business. It's the same thing I can in the electrical systems as well, that everything that I think affects the response of the system reflects in the electrical measurements. And so if we just make that assumption and then start analyzing those disturbances, right? And then consider that it reflects everything that affects the system, then the rest is all about identifying what is expected versus not expected. So for us, images and on all that, again, they are supplementary. Obviously, they add additional degree of certainty at additional cost, right? But the first and foremost indicator that a foreign object coming in contact with a line has got to be reflected in the electrical signatures. And that's what we measure in, not necessarily even voltage, because the voltage is stiff and most of the time, and it won't budge. And in fact, if it does, it can be many, many different reasons. But when you look at the transients and the current, that's easily changed, and the loads can affect that and easily perturb, so to speak. So I think that's really what we are keen on, that any foreign object coming in contact with line will produce those signatures, and there will be some correlation with weather, for example, and it will keep repeating. That's another thing. Again, you're not looking for a single incident, you're looking for some repeated pattern over time.
Yeah, thank you so much. Yeah, that answers my question.
Last question.
Yeah, thank you for the present. Oh, you have one?
No, go ahead.
Okay, nice presentation. I would like to ask, like, is there any plan for utilizing this entire infrastructure for doing some kind of grid edge, like demand response management? Is there a plan, or how do you look at that? I would like some kind of feedback on it.
Yeah, I think, obviously, I focused on, use cases that are, I guess, leading the commercial deployments, and where we kind of introducing sort of novel applications or novel solutions, so to speak. When it comes to demand response and other use cases that's within the general category, I guess sky is the limit. As I mentioned earlier, theoretically, all measurements are good, and you can, with the proper attention and processing, you can motivate similar or same use cases or enhance existing application. I did not talk a whole lot about those things because, again, I wanted to focus on maybe a little bit the leading edge of this stuff. But when it comes to demand response, oftentimes, one of the challenges is identifying, the degree of compliance, the impact on the grid, when it's exactly happening, and especially where it's happening as well, because a lot of time we kind of aggregate the whole response from like a MV bus perspective, subs, and then if you have more of a distributed generation, well, it gets all of it gets aggregated. So clearly bringing a more vivid and a clear picture of where it's impacting and where it's going to be applied would be an added advantage. And I will say that I think we remain open to those use cases, and a lot of these things oftentimes driven really by our partners and customer use cases, so to speak. And we stay kind of responsive to where the pain points are, and if there is an alternative way of solving the same problem, we can let that problem be solved in that fashion. But obviously, happy to help and happy to hear about any and all ideas that could benefit from these type of measurements.
Sounds good. Thank you.
And also, I think that the whole day made all of these things automated. I think that would be also very challenging task. You have done that one. As I said, I have to talk to you offline later. So we also work on, basically wanted to see that if you give me any different topology, and then how do your software adapt to that one? So basically somebody just deploy these sensors. So I'm not sure if you guys look at it.
Yeah, so I guess when I took on this role, I guess the very first challenge in my mind was, whether we want it or not, in this business, in this industry, right? You can't bait and switch, right? You can't just come up with a solution that only works in one environment, and then you move to the next one, and you just say, oh, we got to do the whole thing again, essentially. So I think purposefully we went after, again, just leveraging what we know about the systems, right? We didn't just do AI and ML in a more traditional way where, people just say, hey, give me all the data and then I'll come up with a model. So for us, it's been a combination of what I'm calling first principles, or in the academia, I see people referring to as physics-informed ML AI. So we actually explicitly program and explicitly state. So it's a combination of actually rule-based, and those rules are as simple as just saying, hey, this is a power system. There is certain things that regardless of what the data is telling you, the physics can be violated. So we built those into the platform. We explicitly programmed those in. So it takes care of the fundamentals and the basics, and those are what I'm calling foundational modules or foundational work that they have high degree of confidence that you go from this utility and that other environment, they won't change, right? A capacitive bank, for example, well, it's got to do phase correction. If you think that it's going to do something different in another utility, it's probably not a cap bank, right? So I think it's what I'm calling the hybrid application of first principles, and then you resort to the AI and ML more for more complex scenarios that cannot be expressed by rules and by physics and by kind of a closed form, explicit languages. Then you let the data to guide your decision-making progress. So if you think about this as a kind of a refinery, right? The raw data coming in and it gets into these distillation column to get to jet fuel, right? There is a foundational pieces that will commonly be applied. And as we go to the more complex scenarios, I think that there will be some degree of variance across the systems. But what we're doing there is making sure that our processes and our modeling is repeatable and automatable, so that all we have to do is just say, okay, well, all we need is like two weeks new data set to tweak things. Fundamentals are the same. We just tweak them, and then voila, you've got the model updated and ready to kind of follow the system response in that new environment. So yeah, it's been one of the key consideration, again, to make sure that it's not just one black box that you don't know what's happening, and as soon as you change the input data, your output is completely off chart.
Well, that was really interesting talk. I really enjoy talking to you. We have to have a box of beer and keep talking to respect your time.
Hey, I'm West Coast as well, so I don't mind. I guess we'll hopefully, if I can make it to the general meeting, we should catch up then.
Yeah, sure. We really appreciate that. That was extremely engaging talk. We appreciate that, and hopefully see you sometime soon. Yeah, thank you.
Yeah.
Thank you.
Thanks very much. Thanks for everyone sticking around. I know we ran over, but yeah, take care, everyone. And all the best with your studies.
Yeah, this day, it seems that they had a midterm, so that's why not too many people show up. But usually, they will watch the recorded version, so hopefully they get it. Thank you.
Right. Awesome. Sure. Thank you, Saeed. Thanks for the opportunity. Yeah.
Sure. Thank you. Bye.
Bye-bye.